So we are starting the lecture. Dear colleagues, I represent Intelligent Systems Laboratory of Huawei Moscow Research Center. And today's lecture will be devoted to fundamental mathematical problems of deep neural networks and related practical problems that we meet while designing and developing our products. Just short words about laboratory. In Moscow Research Center, we have more than 200 mathematical and physical researchers, engineers from more than 8 laboratories. Like, this is not the final picture. We are growing up. And one of these laboratories is our one, Intelligent Systems Lab. We have more than 40 researchers from top universities of Russia, like mathematical and CMC and physical faculty of Moscow State University, under Lomonosov, MIPT, Bauman, Higher School of Economics, Skoltech, etc. Our laboratory works on several directions related to intelligent data analysis. The biggest group that actually closely related to today's report is Video Intelligence Group. We work with video surveillance data, participate in Safe City project, and our Video Intelligence Group deals with facial identification, with the problem of augmenting the data sets in different manners. One of the main features here is to produce photorealistic, high-quality images and video of different objects, including faces. And we also participate in AI chip project. You might probably heard that Huawei announced a series of AI chips to be produced soon to the market last year. And these hardware chips are intended to be like competitive enough to like work efficiently in different domains, including gadgets, including desktops, servers, so they will even support neural network training acceleration, not just inference. The second group of our laboratory works on AI for camera. It's quite similar to video surveillance, but as you know, and as you can guess, power supply for smartphones is significantly less than the one for surveillance cameras. So here we meet challenging tasks, including optimization of high accuracy AI solutions for the target low power hardware. This group works on segmentation, denoising, distortion correction, and other camera-related topics. Also in our lab we have big data group, which works with Huawei Cloud Service and helps with solving graph mining tasks, video compression tasks related to storing big amount of surveillance information, and video surveillance itself. Also, we have small groups working with hardware accelerated image search, again for Face ID system, solid state drive devices based on AI technology, and quantum error correction group, which helps to develop error correction algorithms for quantum computers. And we are building the automatic driver assistance systems group for autonomous driving applications. If talking about video surveillance direction, our laboratory has projects and tasks from the whole, sorry, something happened. From the whole pipeline, starting from low processing information from devices, cameras of different type, camera fusion, panorama stitching, going to object detection, like capturing human faces, pedestrians, cars, and different other objects that may occur on the street. Then we are dealing with recognizing, classification, identification of vehicles, pedestrians, cars, license plates, and estimating different features of these objects based on classical and neural network computer vision technologies. The second stage is understanding of the content of the scene. If you detect object, what happens there, what these people are doing, if there is some unwanted behavior, this needs to be carefully analyzed and detected. Whenever you have features calculated from the detected objects, the challenging task is to search for the given feature vector in a huge amount of information stored in the database. Imagine you have 1 billion of Chinese people. They have faces. Each face has descriptor, and you need to answer who it is in several milliseconds. This is impossible to do in software. So for that, there should be huge, like optimized hardware-based solutions. We also work with encoding, decoding of video information, especially related to huge amount of surveillance data that is inefficient to encode and store if you just use regular codecs. So some content-aware video compression methods need to be designed to encode and store this information in a more efficient manner. One of the main features here is AI-compatible video compression when the target is not the human eye, because not the human will process these videos if needed, but some AI-based technology. So you need to preserve information which is important for the deep learning system, but information which is not necessary, which is redundant from this point of view, can be dropped. And of course, if you have this information encoded, this information, how to transmit it. So we are also dealing with efficient video stream transmission and related topics. Now, after this short introduction, let me switch to the main topic of this report. It's called On Fundamental Mathematical Problems in Deep Learning. You may ask a question, why Huawei, which is a commercial company and produces products to earn money, why Huawei is interested in mathematics and fundamental problems? The answer is simple and not simple. We are looking forward. We are interested in solutions which will be used by the industry, not this year and not next year, but also in 3-5 years from now. Many people say that this convolutional neural network era that we are living in, last several years, is a sort of hype. And that might be true, which means that these universal approximators, neural networks, may be replaced by some other universal approximators which solve the same tasks with the same efficiency, but maybe which are cheaper or faster or better. And that means that as scientists, we need to look forward and research. So we will talk about some main fundamental problems which are not completely solved for this deep learning domain, and some other related topics which we found analyzing issues of our products and dealing with these neural networks in practice. Expressiveness, the first topic that I would like to present. The main question here is very simple. Can neural network of the given class represent with the given desired precision any multivariate continuous function? We can say that this problem is solved. In 1957, Andrei Kolmogorov and his team, Arnold, they proved a universal representation theorem for continuous function. So any multivariate continuous function can be expressed as just finite sum of continuous functions of a single variable. We can consider it as a neural network, and we can call these single variable functions like activations. But they are not practical. If you look at these kind of functions, they are not like ReLU. They are much more complex. So this theorem is a sort of foundation for neural network theory. It may allow us to answer a question that, yes, we know why neural networks work. But it's not practical. More practical result by George Cybenko is universal approximation theorem. There are several different versions of this theorem known. Originally, it was formulated that any continuous function on a compact domain may be approximated by a two-layer perceptron with monotonically increasing, non-constant, bounded activation function. Bounded is a key word here. There are variants of this theorem for unbounded activation functions. So this theorem shows that multi-layer perceptrons really work for any practical task with any given precision. And this is even closer to what we need. There are recent works like Professor Yarotsky from Skoltech proven some promising theorem about similar theory for convolutional neural networks. But it's not that complete, and it's not that practical. What we need from practice? There are several promising novel classes, some of them not very novel, of convolutional and other neural networks like graph networks, capsule networks, binary networks, low precision discrete networks, which may be very hardware friendly. Many big companies invest in memristor-based analog neural networks, impulse neural networks, even create some prototype of chips. From the hardware point of view, they might be very promising, lower power consumption, faster inference. Binary neural networks are very hardware friendly. Binary means 0 and 1 or +1, -1. But we can ask the same questions here. What about expressiveness? Can binary network express any continuous function or not? The same for impulse, for convolutional, for memristor. Even if we prove this theorem, there might be another question. How to train these networks in an efficient way? Or suppose we have fully connected or convolutional network with floating point weights, which works perfectly well for the given task. Can we automatically convert it to some of these classes like binary or discrete, not losing the precision, not losing the accuracy? And how to do this? So this kind of theory and technology is needed to be developed. Problem number 2, convergence. We all know backpropagation method based on gradient descent that is used to train the neural networks. Theory for convergence which estimate number of steps needed to converge or number of steps needed to guarantee the given precision, is being developed for tens of years. Like Rosenblatt and Albert Novikov, they suggested a convergence theorem which estimates upper bound for the number of changes in the update weights for binary classification problem, which is very nice formulated from a mathematical point of view. But what we have in practice you train two neural networks with the same architecture with like different random initialization, and you get different accuracy because you converge to different local optima. And like nobody knows if this optima is close to global or not, or maybe some single global optima exists, but we never can get it because our loss function is non-convex. There is a need in some practical theory for estimating the convergence properties of the practical neural networks, including convolutional ones. Open questions that we have from practice. We have two neural networks, two architectures. We can train both of them on the same data. We get some accuracy. How can we answer this network is better than that one? We know that if we train two networks with the same architecture, they always give different accuracy. And sometimes you can get lottery ticket, it's like 1% better. Sometimes ticket is like 1% worse. How to answer this question, not spending resources, not running an experiment 100 times for each network. How to do it mathematically. How to prevent overfitting, one, to stop the convergence procedure. What is the like mathematically proven way to do it? And of course, if we deal with multiple training experiments which need a lot of resources, how to accelerate this kind of experiments? How to make training faster in a guaranteed way? Maybe by using special weights initialization technique or optimizing the tensor operations, convolutions, like tensor train theory, or how to parallelize the training procedure for different nodes, different GPUs, etc., etc. Problem number 3, like enumeration of the problem is random, no sense in it. Generalization. The question is how to prevent underfitting and overfitting, which is closely related to like estimating of the generalization power, generalization error. Sorry. Suppose we have a curve. X-axis corresponds to complexity of the model. Training set is the same. And y-axis is prediction error. If you work on training data, we converge. But if, like, depending on, the higher is the architecture complexity, the bigger is the accuracy. But if you look at what happens on the unseen test data, if complexity of the model is too small, then we cannot memorize even the training set. That means that we have high error. Then it decreases as soon as we increase the complexity. At some point, we start memorizing the training set and go to overfitting. And if we continue increasing complexity, we have unpredicted high error. How to find this point? When to stop increasing the complexity of the architecture? That's the open question. For classical classification methods, there exists this theory, Vapnik-Chervonenkis dimension. Very nice defined. There is upper bound based on input parameters of the architecture. But unfortunately, this theory is not that practical, especially for neural networks. There are recent papers, like the one from Sanjeev Arora, not sure how to pronounce the name, about upper bounds based on size of the net, number of bits presenting the discrete values of the weights, size of the training data set. But these estimates are also non-practical. You see this O capital. What is the constant? So these estimates cannot be used for practice for estimating that point. And there is a big need in this kind of generalization theory development. Because otherwise, it's like exhaustive search. Whenever you have a new task, new like training data, distribution, you need to search which is the size, what is the architecture. It's like known problem of architecture search. And by doing that, you spend money, you spend resources. So open questions are, how to estimate the optimal number of whatever, like weights, layers of the architecture. What is the optimal architecture? Because architecture can be different for the given task. And there are known projects about like AutoML architecture search that big companies provide in this domain. The same question is for hyperparameters. Even though if you can fix the architecture, you can change loss function, you can change learning rate strategy, you can switch optimizer, you can change initialization method, and everything will change, or may change. How to automatically select the best point in this hyperspace? Not like doing blind search or exhaustive search, Monte Carlo search in this parameter space. And very big and important topic, everyone wants this. How to accelerate the inference. Suppose you have a very good model. It works on your PC or server. How to put it inside the smartphone or smart camera. Here a lot of different methods exist, like quantization, pruning, like some matrix or tensor decomposition methods. But in general, like no technology exists which is universal, can be applicable to any task. Or at least not known. Maybe some companies have it, but don't show it to academia. Robustness is our problem number 4. Recently, it was shown, there's a paper from Christian Szegedy, that changing the input of the convolutional network, for example, changing slightly colors of some pixels of the image, you can fool the network significantly. Your neural network, if the input is out of training distribution, can work in an unpredictable manner. This is related to the fact that real data are on some low dimensional manifold that we don't know. And when we go out, our Euclidean matrix stops working. There are so-called adversarial attacks, and there are special types, black box, white box, real-world attacks. I can show example in the next slides that show how to change slightly the input of the net so that the output changes dramatically. This problem is closely related to a problem of adversarial defense. When we want to change the training procedure or the training data set or both, or architecture in such a way that we guarantee that closeness of like input distributions lead to closeness of output distributions. And for that, we need to know how to measure distance between statistical distributions. There are several methods like KL divergence, inception score, but Wasserstein matrix, which works well for GANs. But in general, all existing known CNN solutions are not robust. The theory needed to be developed. So open questions again. How to train GNN to make it robust by defending it from all known and maybe unknown adversarial attacks. How to compare similarity of distributions on the output. Question that I will illustrate with some pictures. GANs, very popular topic now, generative networks. They are producing nice photorealistic pictures, like dogs, cats, faces, whatever you want. You have two GANs, which is better? Not from human point of view, but from mathematical point of view. This means which GAN memorizes the training distribution better? This one or that one? And as I said, how to learn the topological properties of manifolds for the input data or for the output data or for the training data or both. Some examples from our practice. It's me, and it's my name. This is another guy sitting here. And this is his name, but this is my name. And if you rotate the phone, nothing changes. So, like similar picture, this is darker just because lower light. Like you will not see any difference if you look at these pictures. You put it to the input of the real Face ID system, and it can recognize another person, targeted person, from the image where it's slightly changed. Like the same Face ID system, the guy from our laboratory, he changes, like wears some glasses, and neural network stops recognizing him in a guaranteed way, so that you rotate this paper, you move it forward, backward, change the lighting, it still doesn't recognize. Or you wear another glasses, and it starts recognizing you as the given targeted person that you used during training the image on these glasses. Is it good? I think not, because if neural networks like Face ID systems start being used in practice, like for ATM machines taking cash, you wear the glasses of another person and take his cash from the ATM or whatever. So we need to understand why it happens and how to improve it. I mentioned this kind of GANs. You know that the GAN is being trained with generator, discriminator, which tries to understand if it's fake image or real image. After training, you remove discriminator and just use generator to produce photorealistic image, which memorizes your distribution. And these GANs are very well working now. Maybe someone knows this picture, but the question is, which of these two faces is real, which is fake? Who knows? Right. Both fake. But neural network can learn to produce like these thousands of fake images that you look at and you cannot distinguish it from the real photos. These people never exist. It's not like memorizing the distribution of images. Suppose we have these GANs and want to use them in practice for some practical task. By the way, it's an open question, which practical task we can use them for. We have two cat generators. both are GANs. Which is better? The technology, mathematical technology, which is used right now is looking by eyes and voting. Like, I think this is better, I think that one. This is what is used in practice. But we are mathematicians. Now we need to invent some theory. There is a hypothesis that all real-world images, something happened again. They are located on some lower dimensional manifold than our feature space or image space. Image is like three-dimensional tensor, third-dimensional scalar, and you can suppose you have 100 by 100 by 3 image. This means that it's 30,000 dimensions. But manifold that represents all that images is much lower in dimension. How to unroll this manifold? Because we are using Euclidean distance, comparing images for similarities like Euclidean, Manhattan, whatever, pixel by pixel. If we compare outputs of the GANs, it's also Euclidean distance. If you compare features on the classification network, it's also Euclidean distance. But if you measure Euclidean distance between these 2 points, which are on this manifold, it could be small enough, but if you unroll, it would be huge. Probably this is like the nature of our adversarial attacks and defense. The practical problem that we need to solve, and actually each company needs to solve if we are doing with some classification task, metric learning. We try to formulate it in a mathematical way, maybe not that perfect, but here it is. You have feature space. For each input data, like image, you have a feature vector. And what you do when you make an image search, you just use Euclidean or cosine or whatever metrics in this feature space. And if it's close enough, then this is the class that you search for. This is the topic of the hackathon, so you need to be aware of it, and even picture should be in that presentation, but I will repeat. Suppose we have this two-dimensional space, we have two classes, and they are separated like this. If you use this Euclidean matrix and measure closeness, you may have a problem. But if you change it, like one dimension gets bigger weight, it's already more efficient. In a more general case, we need some function that allows you to replace Euclidean matrix with a more efficient matrix, so that the new similarity function gives you better property to differentiate between different classes. Another practical problem related to features. In this case, regardless if features are produced by a neural network or not. Feature mapping. Suppose you have two neural networks which solve the same task. And they can have the same dimension of output features or different, doesn't matter. What we want is we want to transform feature space of one network to a feature space of another one. And we want to do it in an optimal way, so that like mathematical expectation of difference of transformed features, the original ones, is minimized. For example, in this way. You may ask why it's needed. One example, you have like firmware inside the camera which solve face recognition task or whatever classification task it solves. Network is very good. You already have a huge database of objects with features. And you want to update your firmware. You send another network, but this new network will be in another different feature space. So what you need to rebuild the whole database for the update. And you need to do it each time you have the update in firmware. If you have this kind of technology working, you can just map the features and that's it, and use the previous database. This is just one example. Another topic which may solve the feature mapping problem in a perfect way, called disentangled representations. Currently, when you produce the features for the classification task or some other task which needs features to be produced, if you look at these features, they don't make any sense for you. Just feature 1, feature 2, feature 3. If you retrain the network, it could be different order, different sense. You may ask, like, this is a face. I have left eye. Where is left eye? Is it like feature 1 or feature 2? You don't know. You may measure correlation, and you will find that your left eye is like smoothed and is in 100 features. You train next time, left eye becomes like in another location. How to train in a smart way so that each feature has some semantic space. Like we may dream of solution which like produces features like eye color, skin color, like the features that policemen use to detect person on the street. We know that these features exist because policemen do their job very well. May we train the neural network in such a way that it produces some features making sense. If we can do it, then each time when we train network, we will have the same feature space. Perfect solution for the previous network. And we might also investigate the network like by human, what it does and why and how. Another example of a practical problem, like in this presentation I have 8, but we can continue the list easily. There's like a lot of unsolved problems, unfortunately. Video face recognition. Typically, Face ID system or whatever classification system in computer vision we use is optimized in such a way that it's based on one frame per object. This is done primarily to make it more efficient. Because if you apply your detection, segmentation, recognition, classification solution for every frame, for every object, you may lose a lot of power, and if you have some GPU, you want to use it in the most efficient way. So what is done is like keyframe selection. It's maybe someone of you participated in the hackathon by Sberbank last year. No, last year it was another one. This year it was about this topic. So you need to select the best frame. This is what is done now. But it's not that efficient. If you use several frames, maybe you may provide better accuracy. So the task is, you have set of frames. It might be frames from the same video or from different videos. We know for sure that this is the same person. How to efficiently extract features from this set, not from one image. We can call it image fusion, feature fusion, whatever you want. You may like just be based on features, so you take several vectors of features, do something with them, and that's it, that's your output. Or you may even train some end-to-end multi-input solution based on neural networks. The target is to make it fast, efficient, accurate, etc. So to conclude with, we have a number of fundamental mathematical problems. But for each of these, there are some related, very practical ones, which may help us to produce better, more reliable products. And this slide just summarizes some of them. Most of them are already mentioned. I didn't mention this topic, and this one. Let me just say a few words. Cleanup, like everyone knows that data annotation matters. Annotation of data is typically done by human. Human make mistakes. Neural networks now work better than humans in computer vision domain. That means that the data is always dirty. There is always noise in the annotation, and not only annotation. There could be bad quality data. How to deal with that is we can use smart neural networks, which is already somehow trained, or some other solutions to clean up the data. And this is what researchers are doing if they want to win in some challenge, some hackathon. The cleaner is the data, the better is the quality. Another topic not listed here is about distribution of data. Typically, whenever you collect the training data, not from GANs, but from real world, your distribution is not uniform based on attributes like lighting, age, whatever. And if distribution is not uniform, it's well known from practice that your neural network will overfit for the most popular data in the distribution and will work poor for the long tail data which is not represented well. How to deal with this fundamental problem? Deep online learning. The topic which I think every company is dreaming of. Suppose you have some network which is already pre-trained well for the universal case based on your training set which covers all cases. But then you put this solution in some device like smartphone or camera which is located in some concrete place, in some concrete province with concrete like angle of view, concrete lighting, concrete people going through this camera, which is a sub-distribution of the whole training set distribution. From logical point of view, if you want your solution working better for this concrete case, you need to fine-tune this network for this concrete case. How to do this? Not violating the privacy rules. You cannot get data from this camera back from the customer. It's not allowed by law. Maybe you can do some online learning. This is the topic. Fine-tune the network inside the device based on input information that it has without storing, without like, sending it anywhere, so that your network becomes smarter and smarter as it like, looks through the camera and gets information from it. And these are just several small examples that may allow to solve practical problems in a very efficient way. Okay, now I'm almost done. I would welcome questions, but before that, let me just first introduce myself again. If you have questions, you can send them also offline. I'm director of the Intelligent Systems Lab. This is my name, and this is my email. And also, I was asked by our colleagues to show some additional slides. We are hiring. Like list of groups are already presented, so we have many open positions, including interns, senior researchers, junior researchers, summer internship, looking for smart mathematicians, data scientists, etc. Huawei invests in Russia and wants to grow. No comments. And we have VK account. You can also photo this, where we share some information. This is email for sending CVs in general, but if you select our direction, it's better to contact me. And this is our HR manager, who came in time.
Contact personally, actually.
Yes, and you can contact Anna personally after the lecture. I already presented the slides. That's it. Thank you very much.